This is Chapter 11, Section 3. We're going to introduce you to a few more gas laws. Gay-Lussac's law of combining volumes of gases, Avogadro's law, and we will also look at the ideal gas law, which will be our main focus of this section. And I'll be skipping over some things in the PowerPoint, but the important part on this one is the outline of Gay-Lussac's law of combining volumes of gases, which states at a constant temperature and pressure, the volume of gaseous reactants and products can be expressed as ratio of small whole numbers. And we will get to that within some examples. And right above it, it shows you hydrogen plus chlorine gas yields hydrogen chloride gas. 1 liter plus 1 liter of each yields 2 liters of hydrogen chloride gas. If we were to put the formula in on these, hydrogen gas we've got is H2, chlorine gas Cl2, hydrogen chloride gas, which is HCl, and balanced it would be 2 HCl there. And the ratio of those gases would be 2 to 1 to 2. Then we get into Avogadro's law. Looking at Avogadro's law, it says that equal volumes of gases at the same temperature and pressure contain an equal number of molecules. So sounds similar to the previous one. And we have a formula that we're going to put with this one. And that equation is below. It was something that was briefly shown in Section 2. And as we look at it, V is for volume, K is a constant, and N is the number of moles of a gas. So N is the number of moles of the gas. And it says the gas volume is directly proportional to the amount of gas. Because if we were to rearrange this, get the constant by itself like we did in Section 2, volume over number of moles, that is directly related. We are dividing the variables to get a constant. And going back, the standard molar volume of a gas, we do have a typo in here, but this is, it should say 22.4. There it is, rounded off. But the standard molar volume of a gas is 22.4 liters. That's assuming that your gas is at standard temperature and standard pressure, something that we did cover back in Chapter 9. So you do have that value too. And I believe that value is, yes, it is on our pink sheet for our reference page, is the molar volume at standard temperature and pressure, 22.4 liters per mole. Let's go work out a problem. So starting off with the first one, you'd write this down. What volume does 0.0685 moles of gas occupy at standard temperature and pressure? And we would set up our grid for this, put in our given first. And we are going to convert moles, because it's asking for a volume. Volume is going to be in liters, moles to liters, and that standard number we have for a gas at STP is 22.4 liters per 1 mole. Multiply your numbers on top, divide by the 1, you get 1.53 liters. And then in part B, it says what quantity of gas in moles is contained in 2.21 liters at STP. So again, our given information, we have 2.21 liters of an ideal gas at STP, and liters to mole, because liters do match up here and here, just like moles matched up there and there, so that we can cancel them. And the 22.4 has to go with the liters, the one with the mole, and your final answer here, 0.0987 moles. So now we're moving on, just making sure that you know what the coefficients represent. Coefficients in a chemical equation, which are that 2 and understood 1 right there and the 2 right there. So the coefficients for that reaction are 2, 1, 2. They reflect not only your molar ratios, but also volume ratios. So volume ratios is something new that you can do with those coefficients that we have not covered yet. And you see the examples down below. 2 molecules to 1 molecule to 2 molecules. Another ratio is 2 to 1 to 2 moles, or 2 to 1 to 2 as far as volume goes. And you can use the volume ratios as conversion factors in gas stoichiometry problems, just like you would mole ratios. So again, it gives you the 2 to 1 or 1 to 2. It just depends on how you have your units set up that go with them. So what's attached at the back end, you want to make sure that it matches, and they can be flipped around. And again, there's another example there. Pay attention to the labeling of your substance. So again, just like mole ratios, we can do volume ratios. So please write down this example. We've got propane that is sometimes used as a fuel, and here is the complete combustion reaction. So I would go ahead and start with the combustion reaction. That is propane C3H8 plus oxygen yields CO2 and water, already balanced for you. So the coefficients are 1, 5, 3, 4. And the first part of the question is, what will be the volume in liters of oxygen required for the complete combustion of 0.35 liters of propane? And then we will come on with a second part to this too, but let's go work out the first part. What will be the volume in liters of oxygen required? So I'm going to put a question mark right above here if we have 3.5 liters of propane that combusts. So we've got 0.35 liters of propane that's going to combust. So start with your given information. 0.35 liters of propane. Set up our grid. And we are going from liters of propane. This time, instead of doing the mole ratio, which we in Chapter 9 did our mole ratios, we're going from liters of C3H8 directly to liters of O2, and we're using that step. So we're eliminating some steps here, and we're going to throw in those numbers. So A1 goes with C3H8, A5 goes with O2, and you are ready to solve for liters of O2, and your answer is 1.75. The other question, part B, what will be the volume of carbon dioxide produced? And assume that all volume measurements are made at the same temperature and pressure. So if you have 0.35 liters given of your propane, and now it's asking for carbon dioxide, I'm going to briefly go right up here. You know that is propane on top, so I'm going to put liters of propane on bottom, and it is that coefficient right there. So it is still 1 liter of propane on bottom, and the coefficient in front of our carbon dioxide is 3, so 3 liters for CO2 up top. Again, I've condensed a little bit just so that you can see, and your final answer is 1.05 liters of CO2. Moving on to the ideal gas law. Again, this is one of the more important laws as far as us trying to do some calculations. PV equals nRT. So you've got pressure, volume, temperature. N, again, is moles of gas. You have all 4 of those as possible variables. And then R is a constant. And we'll spend a little bit of time talking about what R is, but you do have out your pink sheet because R was listed on there. So here's one of the derivations for you for our gas constant R. Just a little bit more information about it. Again, R is an ideal gas constant. It does depend on the units chosen. So temperature still has to be in Kelvin, But for pressure, are you dealing with atmospheres, kilopascals, pascals? For volume, are you measuring in liters or milliliters? Moles still needs to be in moles for your N, but with your pressure and your volume, you do have plenty of other options that you can use. So if we rearrange the PV equals nRT equation, get R by itself, at standard conditions, we are plugging in pressure and volume. See, there's that 22.4 liters, 1 atmosphere. Moles, it's a standard per 1 mole. And then standard temperature is 273 Kelvin. And if you do that math, you get 0.082 blah, blah, blah liter atmosphere over mole Kelvin. So you have that's a handful of units that are going on. And we will abbreviate this to 0.0821. And that's how you will also see it on your pink sheet. I'll go throw a picture of that again real quick just so that you can see. So again, we do have the universal gas constant right here, the 0.0821, and you notice it's atmosphere times liter over mole Kelvin. Or we have 8.31, but notice that the units are different. This time for pressure, they have kilopascals listed in. We still have liter, mole, Kelvin, but the pressure unit is different. Therefore, that constant value will be different based on the appropriate units. So pay attention to units. So again, this is showing you some other R values, but I can tell you that the two that we just looked at that are on your pink sheet, those are the two that you're going to see most often. Again, the 0.0821 using liter atmosphere over mole Kelvin and 8.314 liter kilopascal over mole Kelvin. So let's work out a sample problem. What is the pressure in atmospheres exerted by a half mole sample of nitrogen gas in a 10-liter container at 298 Kelvin? If you ask me, well, how do I know not to use, say, the combined gas law equation? Well, that first set of equations that we used in section 2, mass or moles was always held constant. For the ideal gas law, moles might not be held constant, so either you're going to be solving for it, you're going to be solving for mass, which would mean a mole to mass conversion, or it's going to be given to you in the problem. So that is going to be the key to look for it. Plus, you would not be given 2 pressures or 2 volumes or 2 temperatures. So plugging in what we have here, and if you feel better rearranging at the beginning, by all means, rearrange to get the unknown by itself because it is asking for pressure. So I could rearrange, put V to the other side, which means you would divide by volume on both sides to get pressure by itself. So I'm going to start plugging in my known information. Half a mole, that's going in for N. I see 10 liters. Well, liters is volume. Notice it doesn't tell you volume, but you have to recognize liters as volume. So 10 liters. It did say what's the pressure, so we are solving for pressure. And temperature is 298 Kelvin. Again, if they had given it in Celsius, you would have had to have converted to Kelvin. So 298 Kelvin. Now, based on that, I have 2 different R values to choose from. Well, when I look at my units, I have liter, mole, and Kelvin given, and both of those R values contain that, but it does say solve for pressure in atmospheres. And the R value that contains atmospheres is the 0.0821 liter atmosphere over mole Kelvin. I'm going to go ahead and rearrange this and get pressure by itself. So divide both sides by 10 liters. So that cancels. I'm left with pressure. Notice that, I'm going to show you how all the canceling takes effect. Liter cancels with liter. Kelvin cancels with Kelvin. Mole cancels with moles. That's great. I am left with atmosphere as my only unit in the numerator. And since we're solving for pressure, that is the pressure unit we're looking for here. So in your calculator, it's 0.5 times 0.0821 times 298 divided by 10. And your final answer is 1.22 atmospheres. So again, be aware. They could have easily had a problem that said solve for mass or given mass, and there would have needed to be a mass to mole conversion or mole to mass conversion depending on how it was set up. So in a nutshell, we have the combined gas law equation. Combined gas law equation can be used for Boyle's law, which means you would mark through temperature. It can be used for Charles's law, which you would mark through pressure. It can be used for Gay-Lussac's law, which means you'd mark through volume. Or again, if you have all three variables going on within your problem, you would leave all 6 of those in there and solve for your unknown. And then our other major one is the ideal gas law. Again, there's not 2 pressures or 2 temperatures or 2 volumes, but we do have a constant, which is R. You have 2 values to choose from, and N, which is the number of moles. And like I said, I know that deals with moles, but if mass were given in grams, you would do a mass to mole conversion, or maybe it wants you to solve for mass. If you solved this equation for moles, then you would go from moles to mass for a second step to get your final answer. So there are the 2 main equations that can represent multiple different laws.